So the next section is about classifying matter. So we talked about what is matter. It's something that has mass and takes up space. But we have to be able to classify things if we want to be able to communicate them, about them effectively. So there's really two categories for classifications of matter. And one is that something is a substance. That basically means that it's pure. So if I have a sample in my hand of a substance, that means every tiny particle that's made up of is the same as the particles next to it. There's only one thing because everything in there is identical. So substances can be either elements or compounds. So if I have a sample of carbon, that's an element on the periodic table. That means every atom in my sample is an atom of carbon. So that's a pure substance. It would be pure carbon if there's no other elements in there with the carbon. You could say that about any element on the periodic table. So it's a pure substance if it's a single element and it's only made up of one element. It gets tricky, though, for compounds versus mixtures because a compound combines two or more elements. So an element is just one of the substances on the periodic table. So if you have a sample of an element, that means all the atoms in that sample are made of the same element. A compound is two or more elements that are connected in a specific way. So in a compound, if there's carbon and oxygen, if they are connected through bonds, then they form a compound. If they just happen to be in the same container, even though they're not actually bonded together, that is a mixture of elements. Okay, so the difference between a compound versus a mixture is that a compound involves bonds. A mixture just involves these substances that happen to be in the same container. So if I take carbon, like graphite, and I just have pure carbon, I put it in a container, and then I add an oxygen atmosphere, well, the carbon solid and the oxygen gas are just both in the same container. So that's a mixture of carbon and oxygen. If, however, the carbon and the oxygen bond together over time, and the carbon and oxygen get connected and make something called CO2, or carbon dioxide, now they're bonded, so that becomes a compound. So you can have a mixture of elements where the elements are not bonded together, or you can have a compound made of elements where the elements are bonded together. If you have a mixture, it's not called pure. It's not pure because you've got more than one substance in there occupying that space. If you make a compound, it could be considered pure if this unit involves one carbon and two oxygen. That unit is the same as every other unit around it. You've got pure CO2 or pure carbon dioxide. Okay, so pure substance is either only one element or a situation where you've got these units called compounds where you've got more than one element connected together in a specific way and every unit looks the same as all the neighboring units. That's what a pure substance is. A mixture is where you have any combination of more than one element that are not bonded together, or one compound in an element, or one compound in a different compound, and they happen to be in the same container, but those different substances are not bonding together. So you could have a mixture that involves carbon dioxide, oxygen, nitrogen, argon, and that would be like air. Right? The air around us, mostly nitrogen, but there's also oxygen, there's also carbon dioxide, there's also argon, there's other trace amounts of other gases, so it's a mixture. It's not all one substance. So that mixture could be then so you've got pure substance, you've got mixture. Once you're in the category of mixture, that can be broken down into two other subcategories, homogeneous or heterogeneous. The difference here is how thoroughly and evenly is that mixture mixed. So if you have air, like the air in the room, that's homogeneous. right? Because if I take a sample of the air, that sample's got the same amount of nitrogen, oxygen, carbon dioxide as this sample over here does. Because everything is thoroughly and evenly mixed in the air. So that's homogeneous. Homo means same. Heterogeneous mixture is one that's not uniform throughout. So some examples of heterogeneous things are things like trail mix and chicken noodle soup, where you can see that some things in that mixture are clearly different from others, right? The noodles are made up of something different from the chicken. So if you can see with your eyes that there are sections that are not uniformly mixed with other sections, it's still heterogeneous. What if I took the chicken noodle soup and put it in the blender for an hour? Would that still be heterogeneous, or would it be homogeneous? So that would still be heterogeneous. A blender can chop the noodles up into tiny pieces of noodles, and it can chop up the chicken into tiny pieces of chicken, and you still have the broth. But it's not going to break things down to a molecular level. Right? So to be considered homogeneous, the individual atoms or compounds that are present in that mixture have to have the freedom to move around and stay evenly mixed. And so if you've got chicken noodle soup and you cut that up into chunks, and you look at the chunks that have been cut up into, you can still, with a microscope, look into those chunks and see that there are tiny pieces of chicken that have a different mixture of compounds and atoms in them that's different from the tiny pieces of the noodles. Okay, so to be homogeneous, the substances have to be mixed thoroughly and evenly on a very, very microscopic, small level where you can see the individual molecules and compounds with freedom to move around and mix in evenly. So that's a little bit tricky. There's a little bit of a gray area between homogeneous and heterogeneous also that makes it a little bit more challenging. So let's talk a little bit about states of matter, because when we're thinking about homogeneous and heterogeneous, it's helpful to have a mental picture of what these particles look like when they're in samples and how they're behaving. So you probably know the difference between solids, liquids, and gases. In a solid, most solids are crystalline, which means organized. So the individual particles are lined up in rows and columns in a three-dimensional arrangement that's organized. There are also solids called amorphous, which means it's still a solid because it's not flowing around like a liquid, but it's not an organized solid. So an amorphous solid is basically like a liquid that was like frozen quickly, right? Because in a liquid, things are flowing around, they're moving. It's not organized. They have the ability to flow around and move past one another. If you just freeze frame that, it's going to have that disorganization that comes from the flow, but there won't be any flow. It will stop flowing. That's what an amorphous solid looks like. In a gas, there's a big difference, because in a gas, the particles are not close together. They're farther apart. So knowing the behavior of the particles in a solid, liquid, and gas, we could come up with a hypothesis, which would eventually become a theory, that would say that in a solid and a liquid, there must be some attraction between the particle and the neighboring particles that are surrounding it that hold those particles close together. Especially in a liquid, right? Because if the particles have flow, that means they can slide past one another, they can move around. Why would they all stick together? If they're able to move around, why wouldn't they eventually move apart and disperse that liquid in around the room? Why would it stick together? It sticks together because there are interactions between the particles. We'll talk much more about that later in the semester. We want to understand why liquids and solids have the particles close together, whereas gases, the particles are far apart and they're moving more independently. So to get more of a mental picture of this, let's take a look at some of these simulations here. I'll dim the lights even a little bit more so you can kind of see this. So I'm going to hit play on this. Oops. So what state of matter does this look like to you? Good. Everyone said solid. That's good. So when a solid, in that picture on the other slide, it was just sitting there. Okay? Kind of gives the impression that a solid, the particles aren't moving. But that's not true. There's always motion. Unless you're at 0 Kelvin, but you can never be at 0 Kelvin. So there's always motion. So these particles aren't really flowing around past one another much. They are kind of moving a little bit, though. So it kind of looks a little bit like a liquid. You do have something that's kind of a cross between a solid and a liquid that's kind of in that gray area between there. And that would be a very viscous liquid. So viscosity is a property of a liquid that prevents it from flowing. So the resistance to flow is what viscosity is. So you can have a liquid that flows really, really slowly. It's basically behaving like a solid. That's kind of what we have here. But it's sticking together because there are attractions between the little atoms. So if I increase the strength of those attractions, it makes it harder for them to flow. And if I decrease the temperature and there's less motion, then it makes it really hard for them to flow. Right? So the temperature is a measure of how much motion there is in those particles. So things are more likely to be a solid at a lower temperature because there's less motion, and they don't have the ability to break away one particle away from the next to form a liquid and flow around past one another. The attractions between the particles and the temperature are really the two main factors that determine this state of matter for a substance. Right? If I have something that's a solid, it's probably because the particles have good, strong attractions between them. If I increase the temperature and it stays a solid, there must be really strong attractions between these things. So I'm guessing, though, eventually here, if I increase the temperature enough, the attractions are not going to be able to hold together too well. So this is much more like with liquid now, because there's enough attraction to kind of hold it together as one blob, but they're still able to flow around past one another. If I decrease the strength of the attractions, and we'll talk later in the semester about how to predict what the attractions will look like, now there's much less. Now it's to the point where once in a while you see an individual circle kind of floating off on its own. So this is kind of a liquid that would be considered volatile. Now the word volatile is, in the English language, it means something different from what it means in chemistry. Right? If you think about the word volatile, you probably think that means that it's unstable. That's not the way chemists use the term. The way chemists use the term volatile is that it means something will evaporate given time. Right? So if I have a cup of water and I put it out here and I wait long enough and I come back, all the water is gone, right? Because it all evaporated. That's because water is somewhat volatile. If I increase the temperature, the water evaporates faster. It's more volatile at a higher temperature. Why? Because at a higher temperature, I'm giving the particles more motion. They can break their attractions they have to one another, and they can fly off as individuals. So that's what I'm talking about here. When the attractions between the particles are not as high, and I increase the temperature, once in a while one of those particles will fly out. And if this container isn't sealed, it'll just go off and be in the atmosphere. Eventually all the particles will have the opportunity to separate from one another. What else do we notice when we increase the temperature about the motion of these particles? They're moving faster on average, but there's still some that are moving a lot faster and some that are moving a little bit slower. It's a key thing to think about. When you think about temperature, from today forward, when you think about the word temperature, make a mental picture in your mind. Think about these particles moving around. Higher temperature means they're moving faster. Lower temperature means they're moving slower. But there's still a distribution of speeds for the particles. So even at a higher temperature, I still have some that are moving slower. Those are the ones that are still going to be held in by their attractions. That's why when I boil water, when I hit the boiling point, it doesn't all suddenly evaporate all at the same time. Because when I hit the boiling point of water, some of the water particles are moving fast, and they have the energy to escape and become a gas. Other particles are still moving slower, and so they stay with the liquid. So it takes a while for it to evaporate because there's a distribution or variety of speeds. Some of the particles are moving fast, some are moving slower, but when I raise the temperature, the average speed goes up. Everything is moving. So whether the type of motion could be It could be like a gas, where the attractions are so minor that when the particles get close together, they just bounce off as if there's no attractions at all. That's how a gas behaves. Or it could be like a liquid. So magma and lava are both examples of a liquid. And in the liquid, there are enough attractions to hold the particles kind of close together, but they're still able to flow around. Or it could be a solid, where if you're at a low enough temperature and the attractions are strong enough, everything is kind of stuck together and nothing is evaporating, nothing is coming off, none of the particles are able to leave on their own. But there's still motion, there's still some vibration. See, I like this because the temperature scale goes from low to high. It doesn't go to 0. You can get to 0 Celsius and negative degrees in Celsius, but Celsius is not an absolute scale. Right? So when we're looking at temperature in chemistry, we like to think about the Kelvin scale, because the Kelvin scale, when we're talking about 0 Kelvin, we actually have 0 motion, because temperature is a measure of these particles' ability to move around and have motion. So if I have no motion, I have 0 Kelvin. But you can't get to 0 Kelvin as far as we know. No one's ever reached 0 Kelvin. So even at super, super low temperatures, a fraction of a degree Kelvin, there's still going to be some motion for the particles. Any questions about that? Okay, so there's another simulation here. This one's kind of cool. So this one also, again, even at a low temperature, if I cool this down, the particles are still moving slowly. So what do we have here? Solid, liquid, or gas? What type of solid?
Water.
Water. Right, crystalline. Right. So in the other one, this isn't like an amorphous solid, right? Because the particles are not lined up in rows and columns. If I line them up in an organized way, now it's like a crystalline solid. And that would depend on the orientation that they have to get into in order to make the attractions between the particles. Sometimes that forces them to organize in a specific way when they become a solid. So I'm dealing with neon here, which is normally a gas. So this must be a really low temperature, 13 Kelvin. That's really low. That's like negative 250 some degrees Celsius. That's really cold. So I've got a very low temperature here. So if I want to make this phase change, make my solid into a liquid, I've got to increase the temperature by adding some heat. Now I've got a liquid. Again, I really like this one as well because it really also does a great job of showing how some of these particles aren't moving that fast. And some are moving a lot faster. So the temperature tells you the average speed. They're not moving so fast that they all break their attractions, but some of them can. Right? So there's a distribution. On the very high end, there are some moving really fast, and on the low end, there are some moving really slow. And it also demonstrates how sometimes a fast-moving one will come in here and collide with something and transfer its speed to another particle sometimes. So at 30 Kelvin, I've got pretty much a volatile liquid, a liquid that slowly would evaporate if I took the lid off because the particles, the fastest-moving ones, can break their attractions and move away. And then if I heat it up more, I can break all the attractions. And once I break the attractions and the particles are kind of evenly distributed, moving around to the point where they're not really attracting anymore, now I have a gas. And when we form a gas, which is basically at this point here, now there aren't really any significant attractions between the particles. Not because they can't attract, but because they're moving so fast when they collide, the speed overcomes the attraction, they just bounce off one another. So when we're talking about pure substances and mixtures, those two demos that we just looked at were for pure substances. So all the particles, all the circles had the same color. They looked exactly the same. So that's a pure substance. Everything has the same identity as its neighbor. So when I have a mixture, though, I can mix things together. If I mix them evenly and thoroughly, that's homogeneous. If I don't, then it's heterogeneous. So what type of mixture do I have here? This is heterogeneous, right? So if you can see with your eyes, it's definitely heterogeneous. I've got sand, I've got iron fragments, and they look different. I can tell that, there are areas with different identities. So with a heterogeneous mixture, sometimes it's not too challenging to separate the components of the mixture. I just use a magnet that pulls most of the iron out of the sand because it's magnetic and the sand is not. So let's look at a couple more examples. 1.8. Actually, that one's pretty straightforward. Let's skip that one. Let's go to 1.9. So 1.9, I want to classify these examples as a pure substance, homogeneous mixture, or heterogeneous mixture. So A is seawater. So seawater, first thing when we look at these ones is to think about what is in it. Can I think of more than one substance that's in seawater? If so, it's not a pure substance, it's one form of a mixture. So what's in seawater? Water, what else? Salt, what else? Organisms, tiny organisms. Yeah, so I've got at least two things. All I really need to recognize is that there's water and there's salt, and water and salt are different substances, so it cannot be a pure substance. It's got to be either a heterogeneous mixture or a homogeneous mixture. And that would kind of depend on how clear the seawater is. Right? So if I've got seawater that's got particles in it floating around, if there's any plant life in there or animal life, that's going to be heterogeneous. It's not going to be thoroughly mixed. If I take a small sample right from the top and there's nothing floating in it, no particles of dirt or dust or anything, and it looks very clear, then I could consider that as a homogeneous mixture, because the salt would be thoroughly mixed in with the water. Yeah, turbidity is a measure of how cloudy something is, right? Good. Helium gas is it's a pure element. Just helium is all by itself on the periodic table. If I only have helium, then that's a pure element. Salt is it's a pure compound. Salt actually is a word that describes a category of compounds. So maybe I'll mention that. When you use the word salt, that describes any ionic compound. So table salt is sodium chloride, but generally the term salt refers to anything that has a metal. It doesn't have to be sodium, it could be any of the other metals on the periodic table, with some quantity of positive charge associated with it, and a nonmetal from the periodic table, or a group of nonmetals from the periodic table with a negative charge. And so because those have opposite charges, they attract and they stick together. So one example is sodium chloride. It's a compound because there's more than one element involved. If you have only metal elements, it can't be a salt. So you need a metal and a nonmetal, more than one type of element, stuck together, bonded together because of the charges associated with them, cause them to bond together, so that forms a compound. Diet Cola. So in a Diet Cola, there's water, there's a dye that causes it to have the cola dark coloring, there's a fake sugar, there's probably caffeine. So all of those things make it kind of sound like a homogeneous mixture. It's definitely a mixture. Whether it's homogeneous or heterogeneous, though, is going to be determined by whether it's carbonated or whether it's flat. So if I say Diet Cola, you probably would assume that it would be carbonated, right? That would make it heterogeneous, because the bubbles have a different constitution. They're made up of different substances than the liquid surrounding the bubbles. The bubbles are basically just carbon dioxide. So you've got carbon dioxide in this carbonated beverage, and you've got the liquid part of the beverage. The carbon dioxide is not evenly and thoroughly distributed in the liquid. It's sequestered into these bubbles that are separate from the liquid. And so that makes it heterogeneous. The bubbles would have to all burst, and the carbon dioxide individual particles would have to be thoroughly mixed in the liquid for it to be homogeneous. Milkshake, that's heterogeneous. It looks thoroughly mixed, but on a microscopic scale, you can see in the milkshake there are going to be globules of some particles that are different from the other particles around it.
So milk itself would be...
Milk itself is actually called a colloid. which is like kind of like halfway between heterogeneous and homogeneous. It's difficult to classify. Probably for the purposes of our class, if I gave you that on an exam, I would probably grade you based on the explanation for your answer rather than whether you put it in one category or the other. So probably you could say milk is heterogeneous, even though it's called homogenized, means it's homogeneous. It's homogenized to an extent because you don't have any large particles of fat like floating on the top like you would have in milk that came right out of a cow, but it's not going to be homogenized on a microscopic scale, and you're still going to have globules of fats and proteins that stick together and are not thoroughly mixed in with all the rest of the water and components of the milk. Bottled water. That would depend on whether it's mineral water or whether it's distilled water. If it's distilled water, it should be a pure compound, just water, H2O. But if it's got minerals and ions and stuff in it, dissolved in it, then that would be a homogeneous mixture because it's not just one pure substance. There are other things mixed in with the water. And concrete is a heterogeneous mixture. Gold is an element, pure element, and nitrogen is a pure element.